The initial term is this, all K is your speed, your gravity and spin and the same stuff, but you also add your thermal term, friction. That's a complete equation. So this everything you can plug in back. So I can also make one other relation like K final minus K initial. That's one term which is coming from delta K plus U final initial, that's coming from delta U SP plus UG final minus UG initial, that is delta UG plus delta ETH is equal to 0, not 0. Basically you have this term, you cannot make it 0 because the term is pretty much friction term. But what I would say, if you line up again delta K plus delta USP plus delta UG plus delta ETH, all is equal to the work. So that's the work energy theorem again. Because there could be possible that some object is hanging by a spring, so it affected by both spring as well as gravity, and then there may be a friction due to drag, then also you can have this. So pretty much that is defining the connecting between previous chapter and this. When you want to have this conservation, you should not have the thermal energy. So this is pretty much without thermal energy, your mechanical system is conserved, the potential plus kinetic term. Therefore, you put all this energy transformation within the isolated system, then you can say delta E is all the changes in the energy is 0, but outside there may be some work you're doing on the system and outside. So here the outside is a energy transfer, but inside is energy transformation. So there's a fine line between transfer and transformation. So you are doing some work onto the system, but within the system there is a change. So that's a cool stuff, right? Because work is equal to delta U plus delta K plus delta ETH. But all this collectively you are doing some work that makes a change in energy, and this change in energy also can run. So think about this. Basically, okay, just mechanical motion, you do some work that creates some energy change. The mechanical energy changing to chemical or other energies, and then you are producing electrical energy. That electrical energy does probably lighting or any other thing. So it's more like a work and energy or interrelated with this concept. Therefore, you could write as one conservation without the friction. That's a energy conservation. This one is with the friction into this. That's still valid for converting to the work. If any friction, that also does work. All right. Okay. Sorry for the writing here, but I want you to take a piece of paper, right, and start working on it. I tell you this problem, and I try to get the answer. This is a pendulum. The pendulum is created by attaching one end here. The length of the string is 78 centimeters, that's 0.78 meters. to the ceiling, and the mass of the pendulum is 150 grams. The ball is pulled back until 60 degrees. That's an angle. From the vertical, then released. So now you are keeping at the position y0. That's the initial position, and then you let it go. It goes to swing, so it goes to the very bottom. What's happening here is the potential energy is 100% at this position. Why? Because the velocity is 0, so no kinetic. All coming from your potential height, the height. So that is 100% potential here. And you swing back. Here the potential energy is 0, whereas you get your velocity. The velocity is this. So you are supposed to find out the V1. The Y1 is 0. But don't rush to solve this problem, because now it is a new height here. What is the length? This is the length of the string. But you need to calculate, this is the length L cosine 60, because we are at an angle. And then if you go this way, then total length minus L cosine 60. So that's a one thing you need to know, that how you can trigonometrically you can get this length and take this one. The reason is you need to find the height from 0, y1. This is a y1. That's a new y1 is 0. What you line up in this equation, the transformation, you go with the kinetic energy, final potential energy, final kinetic initial potential initial. Alright. So now I want you to plug in the numbers. The V1 is the one you need to find out. The Y1 is 0. The V0 is 0. The Y0 is already, the Y0 is the one you need to get from, of course it is calculated here, but you need to know that what is the height of this Y0 that is coming from this relation. So check if you get this. That means 2.8 meters a second V1. So your problem may or may not give this relation. So once they give the original length of the string, then you need to convert this, or at least to do the relation. Get it? All right. Did we see this? Okay. Here is a concept again. 3 balls are thrown from a cliff with the same speed but different angles. We have seen some chapter like this. Which ball has a greater speed just before it hits the ground? At different angles. Yeah. It's simply think about all the three the balls. The ball is at the same height it is dropping. So when it is, even angle doesn't matter, because all the energy is converting from mgy to 1/2 mv squared. In fact, mass is out, so the g is constant, and all you have the y and the v squared. So all three angle is nowhere in the picture. So that means you don't need to worry about the angle. The ball is at this height. Even if you throw this, the speed is the same. So the right option is all the balls are the same speed. all I need to have. You got it? Okay. So the height is matter rather than angle. If we are not talking this in this chapter, if you go back to chapter somewhere the angle was important, then I would say A. Because if you go too much height, then it takes, I'm not sure that it goes, then it's kinematics. I'm telling. We are not solving this problem in kinematics, but we are solving this in energy transformation in this chapter. Yes.
I don't understand why it's not ball A the answer.
Yeah.
What you have just said, why ball A is not the answer?
Yeah.
I don't understand why.
Why ball A is not the answer?
Yes.
The simple reason is all even this angle, we are not looking at the range. We are not looking at the range. If it is a range, then probably A is closer because the angle makes that. But we are talking about speed. The speed is governed by the height at which you are dropping. So even though if you have three different angles, then probably the speed will be governed by gravity maybe, and then the energy transformation. Because you want to have energy conservation.
Well, doesn't C have the maximum height because the angle is going up?
Yeah.
So then wouldn't it be C?
So, but the speed is the same. Even though if it goes to maximum height, transformation of the height to the speed is the same.
Okay.
Yeah. All right. So you have a hockey puck sliding on a smooth ice. So that's already having initial speed of 4 meters per second. Comes to 1 meter high hill. Will it make it to the top or not? So all you need to line up the equation and then try to get whether it reaches the 1 meter, or if you get less than 1 meter, the answer it won't make it. It won't make it. If it is more than 1 meter or close to 1 meter, that should make it. I want you to calculate for, you put the initial speed here, masses cancel in this equation, then you can get your y1. What do you get? y1. No.
Is it just one?
No, we are not putting the one, that one.
Oh, okay.
We are finding the one. We are finding the one. So 1/2 v sub 0 square over g. Huh?
8.
v0 square, make a square over 2g. So 4 square over 2 times 9.8. How much is this? Then decide. Okay, so there's a down there, comes down. So it won't make it based on the number what you get. It should be less than 1. Okay, so that means you need more speed to reach the height. So that's 20 meters a second square. That's speed. Or you can also do the other way. You can put the 1 here, you can find the velocity.
Yeah, that's
Then
what I
you
was
get-
thinking in my head.
You can do either way. You can find the velocity and then see that 4 is valid or not. Right? Alright, this is a very important. We have, in the last class, we did talk about the energy bar chart. Energy bar chart is trade-off between the kinetic and potential as a qualitative analysis. This is called the energy bar diagram. Energy diagram. What is this about? I have the x-axis which is based on the height. You may think that why I put y, why not x? Because we are talking about the potential energy here. What is the formula for potential energy? Fg y. So if you say Ug1, it is Mgy1, Ug2 is Mgy2. So I lined up based on the y1 is my, so I am throwing from here to up, so that's a new height. This is my total energy, which I think 100%. Let's say this is my total energy supposed to be 100%. And you don't have any drag or anything on the friction while it's motion. The blue line is the one we are plotting for only potential energy, no kinetic energy. Kinetic energy is based on the differences, because E is K plus U, so K is E minus U. So if you know my U, I can get 100 minus of U is my K, because I'm on energy conservation. So so this blue line is the line for potential energy, how it changes when I throw an object from one height to another height. So at the very high, with the zero axis, all my energy is what? At this point, what is my energy? 100% what? All my energy is what? Y0. So if Y0, U0, that means there should be energy, K is 100%. Because all my total energy is 100%. So all are converting to the velocity. I'm not asking to start with the L, rather we start with Y1. That's my place, but you know, like this line is a linear. So at Y1, I mean at this point is somewhere, I would say 30% of my potential energy, and rest is 60 or 70% is kinetic. So I'm not, so whatever the this difference is kinetic. So 30 means this is. And when you are at the very height, you are almost close to potential is 90%. Therefore, your kinetic is only 10%. So that shows that the energy, this is only due to gravitational, not spring. This is due to the height only. So you will be asked to draw this type of graph for any particular situation. Elevator is up or a different position with a different speed. So this is energy diagram. Whatever here 100% is coming from potential. Whatever here coming from 100% is your kinetic. Overall, the total energy is 100%. So we take the combo of all the real situation with the energy bar chart and the energy diagram now. So this is the real-time parabolic, what do you call, the projectile motion of an object. When the ball is at y0 at the ground, there is no y height, so everything is 100% is kinetic. So you get the ball as velocity. But if it goes to the mid half, then it has 50-50. It is 50% height, because the height is this much, and it also in the air for velocity. So whenever you see velocity term, that's a kinetic. Whenever you see the height term, that's potential. Then it goes to maximum height. There is no velocity. Velocity is 0. All your energy is potential. So the height is maximum. Then it comes back, it gets again 50%. So we represent this situation in terms of energy band diagram or energy bar chart. And you can correlate this. At this point, all my energy is kinetic. That means total energy is kinetic. I'm not representing. I'm representing only the potential. The midway, I get 50-50. That means I put 50% here. Rest is 50% is kinetic. In the very top, all is potential 100%. It meets the total points and then back again. So for any energy balance equations, you need to first to qualitatively tell what is going on while motion. Then you can work on the equations similar to what we have done, the free body diagram and the equations. What about the spring? The spring has got, I told you the spring is initially equilibrium, and then it may compress or expand in left and right. So when you work on the spring, this L sub 0 is the original length of the string. That's my original length. But when you do the compression and expansion, it may go to left or right at some distance. So this is again the total energy of the spring is 100% because this is the total energy. Here my spring is L0 because if you remember the spring equation is this 1/2 K delta x square, or you can put 1/2 K instead of delta x square you put x minus the original. The x is your change. The x is a change either to the right or to the left. X minus the original length within parenthesis and square. So that's happening. So when you go on the right or left of the aisle, you will get that potential energy is increasing. When you potential energy increasing, that means potential energy increasing, then kinetic energy decreases like that. But we are not showing the kinetic energy here. And it will meet the 100%. You may ask what is this stuff, extra turf stuff. That may come from the turning point or something. So this is again the potential energy keeps on increasing at some point. If you go beyond that delta x, that's a limit. So this is a limit to meet that. That's why the elastic limit. Then if you go beyond, everything else changes, the expanded too much. It won't come back. It's a plastic limit. Alright, so this is a chart for the spring. How about the energy diagram for the gravity, potential gravity? Sometimes you experience a roller coaster with a different hills and valleys. Then where is your minimum lies? Where is your, you may be unstable, and whereas you may have a metastable. So let's assume that this is a particle starts from the rest. All the particles start from rest is 100%. Let's assume the total energy. It goes down the line, the speed increases. So all the potential energy is converted into kinetic energy down the line. It goes to a valley. The valley is not complete equilibrium, but it will be sort of, you can stay rest because your speed is arrested there. Then you up the hill, your speed is decreased because always decrease. So potential energy increases. You stay there, but that state is not stable. Welcome. So that stage is not stable. Anytime you go to the down the line. So this is a stage. So if you go from the one segment speeds up, that's a down the hill. Go to the valley where you are kind of staying there. This is a slow down. The velocity, whenever I say slow down means velocity decreases, kinetic energy decreases, potential energy increases. Potential energy increases. Down again, speed the line. This is a perfect stage where you are at the 0 point potential energy. So you are not, everything is kinetic now. Then you go to the total. So the total energy, that's why if you design a roller coaster, they need to know that what are the energy levels at each height and how much speed you have to maintain. That's very important to keep that. There is again a transition point at some point where it cannot hold it. The potential energy is keep on increasing because you are at a very natural height. So the next slide shows clearly where you are stable and where you are not stable. So you are stable comfortably at this point, unstable because that's a position where it's pretty much your potential is much higher. You always want you're comfortably sitting, right? So your potential is low, you cannot fall down. I'm also okay, but if I start standing on this table, I may fall down. So it's the height matters, that unstable position where it is. This is a complete equilibrium position, and then you go for further. So the height and then the velocity that gives. Not to read the essay. Let's work on this one related to spring. Again, a spring, this is the original length of the, so before a spring is compressed by a block, the spring is having this much length. The length I said L sub 0 is your original length of the spring. I should have brought the spring from the lab to show you. Maybe on Monday. Friday we are not meeting, Monday. So this is the original length, but you are now compressing with a mass, some block. What happens? When you compress this, it changes the length, right? So it goes from L sub 0 to the Y equilibrium position. That's kind of a Y position. That's where it is, it compressed. So there is a change. How do you plot in terms of gravitational potential energy and spring potential energy? Why gravitational is important? Because of a block. So the block is sitting on this, so your gravity matters. The spring, your spring potential energy matters. Therefore, I will show in the next slide, you are plotting the same, the U-shape parabolic, the parabolic shape spring potential energy showed here, the bottom one. When you are at L sub 0, you are comfortable at the minima, very minima of the potential energy. But when you compress it, what happens? It decreases, increase or dependency, the length. Yeah, decreases. So if decreases, it goes to the negative. Let's say this is 0, so it goes to a negative. So that's a new normal or new length of the spring after the you press it. So that means that is your potential energy. There is a gravitational potential energy. So when you are, so the gravity is based on the potential energy increase, decrease, like that. How do you understand the gravity? So the gravity, we saw that in the previous, it's a linear. whenever there is very close to L sub 0, you are pretty much what I would say, how to interpret this here. Let's assume that's the same thing. Let's assume when you are the y 0, that means here is my y 0 or L 0. All my energy is kinetic, and then when you, that's about the block, not about the spring. So when you are putting this, so the height changes, so you will get the yg, but that's not a matter here. What is matter is what is the length of the compressed spring. That means you need to find the y equilibrium, this one part. One other thing you need to know, whenever you are working on the spring, don't forget you will check your formula sheet, you will see the formula for the Hooke's law. The Hooke's law says the restoring force is equal to what? Minus k times delta x. K is your spring constant and delta x is your displacement. I just say that if you plot a graph, force on delta S, you can get the K. So we have done this one or two example on this one previously. What is essential is how to solve the problem. I just did yesterday, so I did not delete this, but it's good for the time. We can just run through. You are working on the potential energy total. Now potential energy total is both spring and the gravity. So my equation says total potential energy is the gravity and then the spring. You have two different formulas, right? Gravity is m times g times y, whereas spring is 1 times k times this delta x. What is that? You go with the y equivalent, the y eq minus the original length square. That was the one we saw in here before. This one. So that's the same thing. If you have a new length, you subtract it. So I lined up this, but I cannot get until if I do some differentiation. Because I get the total system, so I put a du total over dt, that's a derivative of that. So entire equation you take into differential calculus. I just take mg, so that is one, mg is this one, and this is square, so you differentiate this term, again you get k times the entire thing. So this is why it is to get a linear equation. Maybe this is a one-day problem, you need a differential or derivative of the particular function, because you need to get a linear equation. So that ends up with my y eq is equal to this formula, L sub 0 minus mg over k. L0 is already 2 meters, I put some numbers. L0 is 2m, 2 kilogram and 2 newtons per meter. So you can plug this all, you end up the negative. So that's why you said that it is decreased, that number is decreased, 7.8. So I leave it to you, digest this and then try to, then if you have any questions we can discuss. Why there is a derivative needed? There is a story written here, so you can just look at it. The slope is very important, so that's why the slope is a derivative. Final thing is about your force and potential energy. This is the one Hooke's law I told you. So we are repeating the same stuff. So the force you can get from the same equation, rearrange it, get the potential energy over the displacement, you can get it, rewrite this. The same force equation I showed you here, The force equation is nothing but this is equal to minus delta U. So, for this minus, don't take the minus. When you go for the limit time is 0, then you will get into du over ds. So when you plot a graph potential energy term and then the displacement term, you can get a slope that is your force. This is a very new equation for you. You have not seen this. Force is mass times acceleration, but the force also you can get from the delta U term, delta S, because that's why the Hooke's law is important. The Hooke's law is this, force times delta S, and this is a work. Work is equal to force times displacement. See how unique it is? This is the energy term which is a work, and this is your force times delta S times cosine theta is your work again. So you can get from the potential energy term of this. Do we have anything else to say? I will complete this in on Monday. So we can cover up.
Can you stop that?